Each of us uses antimicrobials every day. Then do we really need a course on something like, how to eat food, how to drink food, how to drink water? So that's the kind of thing this course appears to be. Let me try to convince you that yes, we do. So let's first look at what is an antimicrobial and understand the differences between some terms that we seem to use interchangeably but are not interchangeable. An antimicrobial is an agent that kills a microorganism or inhibits the growth of a microorganism. It could do it for several different microorganisms, that means broad spectrum, or it could just do that for one or a few microorganisms, and that is a narrow spectrum. These could be active against bacteria, virus, fungus, or protozoans. Antibiotics, a term that we use interchangeably, are actually only a subset of antimicrobials. These are antimicrobial substances that are produced by a microorganism and act against another microorganism. Antibiotics are not the only antimicrobials we know. We also have synthetic compounds such as sulfonamides, quinolones. We have semi-synthetic compounds. We have plant-derived products and animal-derived products, which can also inhibit the growth of microorganisms, but those are not called antibiotics. And the term antibacterial is used only when an antimicrobial acts against bacteria, not against other pathogens. History of antimicrobials is not that old, even though if we look at some skeletal remains that are available from nearly 2,500 years ago, people have shown by fluorescence assays that there is tetracycline deposited in some of these skeletal remains. As you know, this antibiotics gets deposited in the skeleton. However, it appears that this was from an exogenous source, maybe from a plant or something that was eaten, or from the environment, rather than used for therapeutic purposes. The real first known use of an antimicrobial was the use of arsenical compounds, which started about 120 years ago. So it's not that old. About 30 years down the line, we had the first sulfonamide. Before the first sulfonamide was introduced, actually Alexander Fleming had found that fungi can inhibit the growth of bacteria such as Staphylococcus, but there was no good way of purifying it. Wars lead to scientific development, and that's what happened during Second World War. Florey and Chain found out a process by which they could purify penicillin. They purified it also from the urine of those who were receiving this drug, and that is how it was first used during the Second World War. However, 1940s was the decade of discovery of antimicrobials, and many new drugs were brought in during that period. So during that period, 40s and 50s, several new compounds came in. It continued through 60s. Some new groups were identified. However, I can share with you that over the last 30 years or so, no new drugs that can act as antimicrobials, particularly against bacteria, have been identified. Actually, if you see the below this timeline are the years when each drug was discovered, and on the upper panel are when the drugs were actually brought into market. So even things that have come in the market in the last 30 years are not been discovered in the last 30 years. They have been brought to market in the last 30 years. Now, these antibiotics or antimicrobials have different characteristics. Each of them or many of them belong to many different classes with separate mechanisms of action and very different spectra of organisms or diseases for which they can be used. Their pharmacokinetics differ. Some of them can be absorbed orally, others cannot be. This volume of distribution, the organs that they go to, whether they permeate into the CNS or not, all this vary. So therefore, based on this, different antimicrobials have different route of administration, frequency of administration, their penetration into different body organs differs, and therefore, depending on what is the route of metabolism, their dose modification in different diseases is also different. Also, their adverse effects are different, and we generally try to combine drugs which do not have the same adverse event. So we don't want to give two drugs, both of which affect the kidney. They have drug interactions amongst each other and interaction with other drugs. And there are interactions that you cannot use more than one of some of these in combination. Therefore, it becomes important for us to choose, to learn how to choose and use a particular antibiotic. And that's one reason why this course is important. Antibiotics have changed medicine. Many diseases which used to be fatal, which used to cause a large amount of morbidity, those diseases, their mortality and morbidity has changed. Acute rheumatic fever used to be a deadly disease. It used to cause cardiac damage, leading to valvular injuries. Now this condition has virtually disappeared from many parts of the world. And even in India, the frequency is much lower today than when I was a resident. Sepsis, mortality has reduced. Bacterial meningitis has become treatable. Some diseases have virtually disappeared from some parts of the world and markedly reduced in other parts of the world. Tuberculosis, syphilis, gonorrhea are some of the examples. Surgery, even though it was done before antimicrobials came in, it was beset with many problems, in particular wound infection. With the advent of antibiotics has made surgery safer and actually possible. Things such as abdominal surgery, where bowel was opened, bowel which has lots of bacteria, was unthinkable before the antibiotics came in. And it is only because of antibiotics that we have gastrointestinal surgeons. Also, they have other non-health uses. They've been used in animals to promote growth, to prevent infections, because if you are able to grow animals better, if they don't die, it is commercially useful, and you can people who raise meat, they are benefited. Also, it has been used for food preservation, something that has been given up because it increases the potential of antimicrobial resistance, and I'll come to that. They have also been used for prevention of diseases. So if a person has bacterial meningococcal meningitis, people around him would be given prophylactic antimicrobial so as to prevent disease. And they have also sometimes been used for non-bacterial diseases, such as we in gastrointestinal diseases use some antimicrobials because of their effect on gastrointestinal motility, etc. The problem with the use of antibiotics is the development of antibiotic or antimicrobial resistance. When we look at any infection, the organisms, majority of the organisms are sensitive to antimicrobial, but during an infection, the bacteria multiply in large numbers, 10 to the power 9 and above organisms are present. And when they multiply very fast, there are instances when there is a mutation in the genome of the pathogen, and some of those mutations, occasional ones, make the organisms non-susceptible to the antimicrobial agent. The problem is not, their number is not very large, but what happens is, because the person is receiving the drugs in the presence of the antimicrobial drug, all those pathogens that are sensitive to the antimicrobial will die off, and only the one that is resistant will live on. It has more resources available, it will multiply at a faster rate, and its number will progressively increase with time. In some cases, actually, they have a survival advantage that they actually gain when drug is present, because commensal bacteria are reduced and these pathogens have a field day. They multiply very quickly to very large numbers. Another thing that happens is, only some bacteria may develop the resistance mutation. Certain species are more prone to this. Other bacterial species may not be as susceptible, but when the different bacterial species exist in the same niche, for instance, in the gastrointestinal tract, those bacteria which have the resistance gene can have, by through the process of conjugation, pass on the resistance gene to other bacteria which by themselves are more hardy and cannot acquire mutations so easily. This leads to transfer of antimicrobial resistance from one bacterial species, one pathogen, to other pathogens, and these can then thrive. It has been seen that when a particular antibiotic is introduced in the population, the resistance is either absent or is very infrequent. However, as the antibiotic is used in the population, the frequency of resistant strains increases. So when methicillin was introduced in 1980s, there was very little resistance among Staphylococcus aureus in uh, against this antimicrobial. But with time, over the next 20-25 years, a large majority of isolates became resistant to methicillin. Similarly, is the case for bacteria that are resistant to vancomycin or fluoroquinolones. The other problem is that the moment it develops at one place, it soon, with current modes of transport, we have seen that with COVID, how quickly COVID spread from China to other countries, and how quickly any new isolate that comes up soon becomes prevalent all over the world. Same thing happens, and this slide shows for uh, carbapenemase resistant and for NDM positive bacteria, how they were seen first at one place and very soon spread to other parts of the world. Also, for some antimicrobial agents, bacteria can develop multiple pathways by which they can be resistant. So for beta-lactamases, there are this group of enzymes called metallo-beta-lactamases, and there are many different enzymes, and a mutation in any one of them can lead to the bacteria being resistant to the effect of beta-lactamases. And therefore, it's a situation that we cannot deal with, we cannot prevent totally. Antimicrobial resistance leads to several important consequences. Here in the front, you see what is the cost of treating each of these 4 diseases in US dollars when the organism is sensitive to the first line drugs. But if that does not happen, and if you need to treat them with alternative drugs, we can see that the costs go up drastically. And that is a problem all over the world, but particularly for countries such as India. If we look at the burden of infectious disease, when we are in low middle income countries such as us, our burden of communicable disease is more than that of non-communicable disease. And therefore, we really are affected by these organisms that become antimicrobial resistant. What determines the occurrence of antimicrobial resistance? This is a slide that on the x-axis shows number of courses of antibiotic that are used per 1000 population per day, and on the y-axis the proportion of strep pneumoniae isolates in a population that are resistant to penicillin. And we can see that there is a positive correlation. Those countries, those societies that use more antimicrobials have clearly a higher prevalence of infections due to antibiotic resistant organic. What happens is that we initially start with a situation such as this, where most of the bacteria are sensitive, but some bacteria, and the person is given antibiotics, some bacteria that are somewhat resistant to the drug occur. Now, this will be taken care of by nature, and these bacteria will soon die off. But when in a population, a large proportion of people are treated, all these antibiotics also diffuse into water and soil and environment. And also these bacteria reach there, and gradually, because of exposure to higher concentration, they go on getting higher resistance, and we get fully resistant isolates. So if you look at this, what I want to show you is we are getting antimicrobial resistance, but in last 30 years, we don't have new drugs, and the whole world is worried. You can see the WHO is worried. The US president made a special committee on looking at antimicrobial resistance, which was similar to the parliamentary committees that we have. Again, US, during COVID, because even though it was a viral infection, a lot of antibiotics were used, and that has made the problem even worse. If we go to this systematic review published about 3 years ago, we can see that there are about 5 million deaths that occur in the world every year where there is bacterial antimicrobial resistance, and fully 1/4 of these are those that can be attributed to AMR, meaning if the AMR had not been there, they could have been treated and saved. The problem is particularly bad in South Asia, where we are. And if you look at from this paper itself, India is particularly bad. For methicillin resistant Staph aureus, 50 to 60% strains in India are resistant. There are some countries that are doing worse than us, but we are quite bad. If we look at Escherichia coli, third generation cephalosporin resistance is present in 60 to 70%. We are easily the hotspot in the world. If we look at Acinetobacter, carbapenem resistance, India has more than 80% resistance. Fluoroquinolone resistant Escherichia coli, again 50 to 60%. And when we go to carbapenem resistant Klebsiella pneumoniae, we are the worst that anybody in the anywhere in the world that it could be, 50 to 60%. Third generation cephalosporin resistance in Klebsiella pneumoniae, again, we have 70 to 80% resistance. So to summarize, through history, infectious diseases have been a major cause of human health disease and death. Antimicrobial drugs were a major advance which improves our survival, made surgery possible, and became soon one of the most widely used group of drugs. However, indiscreet use, development of antibiotic resistance, and a poor new antibiotic drug pipeline pose a major threat to human health, and it is possible that in about 20 years, we'll be back to where we were about 100 years ago. In the above context, it's important that each of us, you and I, understand the appropriate use of antimicrobials so that we don't lose the war to these pathogens. I'll stop here. If there are any questions, I'll take those up. Thank you.